That would have been a shame. So motional EMF, right? A voltage is produced by the separation of charges caused by the force acting on positive charges differently than the negative ones, right? Because one's a right-hand roll, one's a left-hand roll. And why were those charges having a force acting on them? Because they were in the presence of a magnetic field, okay? And they were moving in the presence of the magnetic field. How were they moving? They were moving because we were, right? They were moving because we grabbed that metal bar and it made them move, okay? So the electric field that's created, right? Separation of charges create a voltage. Separation of charges, you know there's going to be an electric field pointing from positive to negative. So that electric field is induced by the motion of the bar, okay, in the presence of a magnetic field. You know, this equation, you'll have to, unfortunately, you probably have it correctly written there, but it got a little messed up. So when the forces, I'll try to rewrite it. So when the electric force, which is QE, right, balances the magnetic force, which is QVB, what happens? So when FE equals FB, FE, you remember, is QE, right? FB is QVB. The Q's cancel. And what you see is that the electric field that's created is a product of the velocity of the bar, which is how you're getting those charges to move, right? You're physically grabbing them by the neck and moving them, times the magnetic field that they're in. So the motion of the wire, or the bar, through the magnetic field induces that potential difference. So remember that E is VB, but E is also a voltage divided by a distance, right? So we can plug in, I'm not sure which version they have, but you can take that electric field and plug it in there. And if you want, we could express the voltage at, let's do over D, as VB, where this is little v, this is velocity, I'll make it script. In other words, the voltage, velocity, magnetic field, and then the distance, or this distance, right? What you could say is the length of the wire. Or not of the wire, but of the metal thing, of that bar. Let's use L. I like L better. D, I like L. Let's use L. Let's use L to denote the length of that thing. Okay, so we're kind of doing a little mini derivation for motional EMF problems. And this is like your first exposure into magnetic induction. As you saw with Faraday's laws, there's different ways, right? You can do magnet in a loop. This is just one of the ways to induce an EMF, okay, which is called using motional EMF. So we're kind of deriving some equations that you can use to solve these types of motional EMF problems, okay? So this is, what I was saying, it's just like a battery. It's just like making a battery out of thin air, or by grabbing a piece of metal and moving it along a copper wire, okay? Whenever you have separation of charge, you have yourself a voltage. Whenever you have a voltage, it's gonna give potential energy to charges and get them to move, right? U equals QV, right? If you give that charge potential energy, that charge is gonna start moving, and thus a current is produced. So that EMF, this is the equation that we just wrote. Instead of voltage, they use EMF, the epsilon, and then the VLB is just however you want to arrange your letters, okay? I like BLV because it goes alphabetical, but they are going anti-alphabet, which is fine with me. So motional EMF is a way to produce a voltage, by a changing magnetic field. Okay? The magnetic field is changing essentially because you're moving that bar in the presence of the magnetic field. I'm just kind of generalizing it. So in this example, let's skip this one and move on to the other geometries, okay? So you're going to use, it's going to be, and then plus it's all screwed up here, so I'm sorry about that. It's going to be using those equations and adapting what's written here into a model, to that model, okay? So, I'm thinking this is just kind of reiteration of, okay, yeah, actually, yeah. So let's talk about the circuit aspect, right? So this current is being induced, and it's gonna, in order for a current to flow, it needs to be in a complete circuit, right? So the circuit then is created by the U-shaped current loop, right? This is like a current carrying wire, and the bar being on top. So the bar being on top of it is the contact, right? They're in contact with each other. So current can flow from the bar to the gold wire, okay? So that's gonna form a complete circuit, and it's going to follow everything that circuits follow. For example, V equals IR, all right? So if we want to know the value of the current, if we want to know how much current there is, we're going to take I. We're going to solve for I, V over R, where R would be the resistance of this bar here. They call it a wire, but I like to call it a bar. Okay? So the voltage created by that EMF, right, VBL, this is voltage V, divided by R is going to give us the current. Okay, so you can treat this as a circuit, even though it really doesn't look anything like a circuit from what you've already seen of circuits, okay? That's what this is. I equals V over R. V is epsilon. Epsilon is little v, BL. Okay, that's what that says. The force. So force on a current in a magnetic field, it's ILB. Okay, so I is VBL over R. We have our LB. So the force is V, B squared, L squared over R. Okay? So that is the force, the magnitude of the force acting on all of those, on that current. Or you can think of it as acting on all of the particles, charged particles in the current. Okay? So maybe you're thinking, how come we're not like producing, free energy with this situation, right? All you have to do is move this bar around and you can generate a current and you can power something cool, right? Well, don't forget that someone has to be there moving that bar. And if not us, then a robot. And if not a robot, then some kind of machine, right? Has to be there to do it. So there is no free energy, even though it seems like we're maybe waving a magic wand and creating current out of thin air. There's no free energy because someone has got to crank it. Someone's got to be in a crank. Someone's got to create the changing field, right? Or the motion in a constant field. So it takes energy, right? It takes a force to create that. And so that's what we're looking at here. Is, when we pull that bar, what we're doing is we're imparting a force to the bar, and what nature is going to do is try to oppose that change by exerting that magnetic force on each of those particles and causing them to move upwards. So the force that we the force that we add to it is going to be in the opposite direction that the charges of the current experience due to that changing force, to that changing field. So the power dissipated, right? So power is energy over time. So the energy of the work done by the force, right? So this energy is work. The work done is force times displacement. Hold on, and that's all over time. Let's keep this. There we go. And we saw we had an equation for force. We plug that in, okay? The distance that we pull it is going to be whatever this distance is here, and then divided by time. So we're not going to worry. I don't want you to worry too much about power. So I'm just kind of explaining a little bit about like the consideration, right? How much power is generated by this? Well, it's going to depend on how much work I'm doing, right, to get the charges to move around. So just a general idea. So don't worry too much about power, okay? I would rather, for electromotive force, focus on the voltage created, the force direction on the particles, and the voltage that's created. So essentially, this is how generators, right? This is how we create electricity. This is actually the only way we know how to create electricity, is we move an object with charge in the presence of a magnetic field one way or another. So here's one way, right? This geometry here looks different than anything I've shown you so far. There's many different geometries. So what I have is like this U-shaped magnet here. So it has a strong magnetic field inside, and then this crank is turning a bar, and it's getting it to rotate in the magnetic field, so technically it's experiencing a changing magnetic field direction. If any aspect of the magnetic field is changing, you're going to get yourself the induced current, okay? And then that induced current is going to flow and light up the light bulb, right? So all we need to do is find some way to move charges in the presence of a magnetic field, okay? And then we can get ourselves electricity. So this is how generators are created. You have like Beaver Dam, right? All sorts of dams, they create energy. How do they do that? Well, they use the water falling a great distance to power the generator, to basically maybe hit some kind of turning mechanism here and cause it to move down, right? They're constantly using the falling water to move something for us in order to create electricity. So we're basically looking at how we create electricity. We create it through essentially mechanical energy, right? It takes mechanical energy, something physically moving in order to generate electrical energy. And we just make that thing physically move in the presence of a magnetic field. So what I mentioned before, right? We've been looking at an object that is in a constant magnetic field. And I've been saying that you can either change the magnetic field to produce this current, or you can change the direction in which the magnetic field is pointing. So that's what I was doing here with this wheeled object, and what this generator is doing, right? The B field created by this north and south pole magnet, that B field is constant, right? So maybe you're scratching your head, well, what's changing with time? Well, if you look at that current loop, the angle that the loop makes with the B field is changing with time, right? As I spin it, as this wheel rotates, like this, right? The B field and the area vector are going to be in different directions. So maybe you're like, what's an area vector? An area vector is the vector we use to describe an area, and we're going to talk about flux, so this is going to come up, right? So if this is a square is, you know, a flat thing, and you might be wondering, how do you assign a vector to it? Well, the way we do it in mathematically is we use a perpendicular vector, and that vector is going to have the magnitude equal to the area of that box, okay? So what's changing here is the area vector in relation to the magnetic field direction. So you can see that this coil is kind of up at an angle like this. So this would be my area vector. This would be my magnetic field vector. And as that coil turns, the area vector is going to be rotating, right? Changing the angle between B and A. Producing an EMF, right? A voltage which creates a current. And if you look, we had a measuring device here, what we would see is that current or that voltage is going to oscillate with time. Okay, it's going to reach a maximum, it's going to reach a minimum, and it's going to be zero momentarily. So we'll talk about that. We're just kind of looking at it qualitatively, and then we'll get into it quantitatively. Okay, why that is. Oh, where's my flashlight? Oh, I didn't right now. Oh yeah, it's here. Okay, this is a battery-proof hurricane flashlight. So there's no battery in here. The only thing inside this flashlight is a copper coil and a magnet. Okay. And I can turn it on, and I'm not going to get anything. If I start to shake it, right, and get that magnet to move inside the magnetic field. See, you can see the magnet moving and the coil. I'm going to get it to light up, right? So I produced a voltage by taking a magnet and changing the magnetic field that it's experiencing by moving it through the copper coil. And then the copper coil is going to produce a current through it and power the little light. And you can see it's getting dimmer and dimmer because there's a capacitor in here that is storing the charge and dissipating that charge over time. So you can see how it all connects together. So that's kind of what this is talking about a little bit, kind of a similar idea. So now let's get in. We've looked at it. We've done a bunch of observations, right? And you kind of just trusted me, and we used the force acting on a charge, moving with velocity in a magnetic field to kind of support this. So now let's get into some quantitative and reasons why this is happening. Okay. So we're gonna look at the magnetic flux. We're gonna define what the magnetic flux is, and then we're gonna look at Lenz's law, which is gonna help us determine what direction that induced current is flowing. Oh, I'm sorry. Well, okay, you can see it from here. Thank you. So let's talk about flux, what flux is. Flux is a mathematical operation, and we'll talk about that. So, but we're going to kind of motivate what we're doing. So, right, you know that Faraday found that a current existed or was induced when we had a magnetic field passing through a coil or a loop. This also happened when we slide that bar along the rail, okay? And so now we're going to define more clearly what we mean by the amount of field, right? We know that the magnetic field was changing, but we need to define how it changes. So we're going to use magnetic flux to do that. So you can think about magnetic flux or just flux in general as how much stuff is passing through a loop. In this case, how much magnetic field is passing through a loop. And you can use the analogy of fan, right? So fans make air move in a certain direction. So you can think of like the little vectors of air, right, flowing. And the amount of flux is going to be like how much air is blowing through a certain area. So what matters is the direction of the area vector, which I showed you how we describe what an area vector is, its relationship to the direction of the vector that we care about, in this case, magnetic field vector. So we'll need to be looking at our loops from the side in order to see it better, okay? Right, because here we can easily see our area vector, which is always perpendicular to the loop. Here we can see it being parallel to our B field. Here, our area vector is at some angle with respect to the B field. So it's going to be customary for you to look at your loop not flat on, but edge, okay, on the edge. And that way you can just see the area vector very clearly. You can also look, front end view, right? It's just a little bit more difficult to visualize the vectors because they're both coming out of the page. And if this blue one was at some angle, right, it's kind of hard to see the angle between them, which is what's important. So we're going to define the flux. So we use this. I'm pretty sure the book uses this letter, capital phi, with a sub b. Okay, this is the symbol for flux. It's the capital phi equals B, magnetic field magnitude, A, area of the loop, cosine of the angle between B and A. Okay, so B, magnitude of magnetic field, A, area of the loop, theta, angle between the B vector and the area vector. Okay, so that is how we calculate the flux. The flux, how much magnetic field vectors are penetrating a particular surface area, okay? So, when the magnetic field is parallel to the area vector, the angle between them is 0, and you get no flux. No flux given. Oh, hold on. No, you get maximum flux. Sorry, you get maximum flux. I was getting excited to use my line. Right? How do I know that? What's cosine of 0? It's 1, right? It's not 0. You get max flux. Sorry, you get maximum flux. Okay? If your area vector is at some angle with respect to the B field, then you're going to get a little bit less flux. Right? It's going to be scaled by cosine of theta. If you are perpendicular, they didn't draw it, but if the area is perpendicular to the B field, which means your loop is parallel to the field, right? This is your loop. So when your loop is parallel to the field, your area vector is actually perpendicular to it. And thus, the angle between them is 90, and cosine of 90 is 0. So the flux in this situation is 0. So it's really easy to get confused with the loop direction and the area vector direction. Okay, the loop direction is one thing, you don't really care about it. The area vector is what you care about. And you know that they're always perpendicular to each other. Area vector is perpendicular to the loop's face, okay? So you can see now, as this loop is turning, there's going to be moments of no flux. There's going to be moments of maximum flux, right? So it's kind of taking the shape of that sinusoidal curve that we saw, right? So flux has something to do with the EMF. We're almost there. Okay, but now you can see that sinusoidalness taking shape, right? Cosine function. So, I'm not sure what this picture is showing me. B cosine theta. Yeah, I was looking at this earlier and I was trying to figure out, I'm not sure what it's showing. There's our picture. Oh, it's showing our effective area. I prefer just using this equation. Don't worry about effective area, okay? There's our equation here. So the units of flux are the Weber. So a Weber is a Tesla, because that's a magnetic field, times a meter squared, because that's an area. So a Weber is a Tesla meter squared. So here are some pictures that we're going to be looking at, calculating the flux, okay? So real quick, let's review on how we find the the angle between two vectors. The only way you can find the area between two vectors is if they're placed tail to tail, okay? So our area vector comes out of our object, and technically the area vector can be anywhere. The area vector doesn't have to be in the middle, okay? As long as it's perpendicular to the face, it's fine. So you want to find a place where your area vector and your B field are tail to tail, like right here. And you can see that the angle between them would be theta. Okay, when you look at more problems, the geometry will get a little confusing. You just need to make sure that your two vectors are tail to tail in order to find the area between them, okay? So, we gotta hurry. Let's do this quick check problem. So, which square has a larger magnetic flux? So, we need to know B, and we need to know A. And the angle is going to be the same, right? Because they're both oriented in the same way as the magnetic field is, right? The area vector is pointing out, and so is the magnetic field. So what we're looking at is how B changes and how area changes. So we see that the field in this case is twice as strong, but the square is twice as wide, okay? So the area of a square is length times width, right? So I'm going to make that substitution. So if the square is twice as wide, let's do flux 1. We'll just call flux 1 B1A1. And flux 2, the magnetic field is half as strong, right? So it's going to be B1 over 2. Why is it half as strong? Because this one's twice as strong. So if this one's twice as strong, then this one's half the strength of the first one, right? And then the area, though, is twice as wide. So each length is twice as long. So we're going to do 2L times 2W. So we get rid of a couple of 2's, but not all of them. We got 2B1A1. So flux 2 is twice as large as flux 1. So loop B should have the larger flux. And that's because the area of the loop, is 4 times as big, right? Even though the B field got weaker, the area of the loop is 4 times bigger than the first area. Okay? Good there? So, let me just kind of skip some of these. Let me see what we got coming up here. Just to introduce it to you so that when we come back next week and talk about it, you'll have it, we can do more of these quick checks beforehand, but I want to talk to you about what Lenz's law is. So Lenz's law tells us what the direction of that induced current is going to be. And so Lenz's law is going to be, we're going to figure this out by another right-hand rule, okay? So we want to determine the direction of the induced current. We're going to use a right-hand rule for direction of current. So this is like an independent one. Okay, this is like a new one, totally new and independent of what you've learned already. So what Lenz's law states is that an induced current exists if and only if a magnetic flux is changing. So now we know what's changing. Like, now we know why with the slide wire generator, why we got a current, even though the B was constant, right? And the A vector was constant too, right? It was pointing in the same direction. Because the area was changing, right? As we grabbed that bar and we yanked it to the right, the area exposed to the magnetic field changed. So we can see an induced current. So, and that's because what really matters is that the magnetic flux through the loop is changing, right? Magnetic flux is B, A cosine theta. So if B changes, we get a current. If the area changes, we get an induced current. If the angle between the two changes, we get an induced current. So now I think all those three geometries that I showed you didn't make a whole lot of sense, right? Why were we still getting an induced current? Because what matters is how the flux is changing. And the flux can change three ways, right? B could change by moving a magnet around and changing how strong the strength nearby. The area can change by doing the slide wire generator, right? Pulling it, increasing the area exposed to the magnetic field. And then theta can change by making your loop area vector change directions. Okay? So those are the three ways you can produce a current, an induced current. And so what Lenz's law tells us is that the direction of this induced current is going to be in the direction that opposes the change. It's kind of like, what direction is it? It's the direction that opposes the change that is occurring, okay? Whether it's the B field changing, the area vector changing, or the area magnitude changing, the direction of the induced current is going to oppose those changes. So we need to kind of practice how we do that in a right-hand rule, okay? So this is what I just outlined in the previous, right, that's this. 3 different ways to change the flux. So, let's look at this case. North pole of the magnet, okay? Going into a loop. We saw that it creates a current, but we didn't know what direction that current flows in these little loops here, right? So what we're going to do first is figure out what direction the current would be according to our regular right-hand rule. And then Lenz's law says that the direction opposite to that is what is going to induce a current. Okay? So we have B going down. So this is how I'm wearing rule. So now, right, we're flipping. B is your thumb. So right, this is a new right-hand rule. B is now your thumb. Your fingers are going to be the current direction. Okay? So we can see that the B field from the magnet is pointing down. Why? Because lines always come out of the North Pole, right? So B field is pointing down. That means that we're going to have a current flow. This is not the real one, but we're going to have a current flow like this. Okay? Looking down at my hand, that's going to be clockwise. What does Lenz's law tell us? That the current that is induced opposes that change. So the answer is going to be opposite to the clockwise. It's going to be counterclockwise. Okay? Because why? Because we're increasing. Are we bringing this magnet down or up? Okay, this one's holding still. Okay, well, we're going to start moving. There's no moving arrow. Okay, this one's holding still, so no current, obviously, right? Boom. All right, there we go. We're moving it down. What's happening? The B field near the loop is getting stronger and stronger. So what does Lenz's law tell us? It tells us that the induced current is created by an opposition to the change. So the induced current is created by the B field that is opposing the change, which we call B induced. This is not a real B field, right? The real one is coming out of the magnet. This is the one that is induced in the opposite direction, creating a current going counterclockwise. Okay, so the right-hand rule, the new one is thumb is B, fingers are I. With the additional fact that the B that we are using for our thumb is the B that opposes the change. Okay? What's the change? The change is a North Pole magnetic field getting bigger. How do we oppose that? We apply a magnetic field in the opposite direction. So we're going to do our thumb in that direction. And watch our fingers move. And our fingers move as perspective matters. We look down on it. Your fingers are going counterclockwise, right? So your thumb, so for the right hand rule, your thumb is in the B induced direction. And the B induced direction opposes what's changing. So it's a two-step process, okay? Step one, B field is your thumb. Step two, how are we gonna oppose the change with this thumb? Okay, so let's look at another example. I think we have one more minute. All right, what about the opposite? So now instead we're pulling the magnet away. The North Pole is still pointing down, okay? So our B field created by the magnet is pointing down. But we're pulling the magnet away, so that means the loop is experiencing a weaker and weaker B field. How do we oppose that weakness? We add more in the same direction, right? How do we oppose the weak B magnet? We did it right, as you bring it away, the magnetic field experienced by the loop is going to get smaller and smaller. How do we oppose that change? We add more field in that direction, right? I'm sorry, in the downward direction. We add more field in the downward direction to replace the downward direction field that's leaving, okay? So our B induced now points down, creating a clockwise, right? Look at my fingers, a clockwise motion, as we do from above, okay? Take some practice. That's why I wanted to show it to you early and give you the cheat rule that I use so that next class we can, really dive into it. So, I don't know if you want to stick around, I'll show you the levitating thing. The Engineering Expo is coming up tomorrow, and this demonstration will be there. Get right closer. Yeah. Let me know if you have any questions.
Yeah.
Crank it. Oh, it's floating, right? That's magic right there. That's how this is here for me too. Fruitio, that is. Right? So, I'm gonna turn it up a little bit. Whoa, it's floating more! Whee! So what's going on here is that, I'm creating a force on this due to the changing magnetic field inside this box, and that force is pointing in a direction that's going to oppose the weight. So that force is pointing up, and it's so much force that it's going to counteract the weight of this, which is not very heavy because it's aluminum, right? We don't, it's hard to make a very strong magnetic field. So,
So you just like levitating?
yeah, so this is levitating, yeah. And so, actually there's some lighter plates there, you can see even more levitation. This one's very thin. Whoa! This is probably what the magicians did,
That's awesome.
Well, the science was still new and no one understood it.
I would think that
Yeah.
Disney or something.
Yeah. Oh yeah, no, they probably do, and they use it in animatronics or something.
Yeah.
what's going on? Who had a question?
So, can I not take the final but take the third exam?
No.
So I have to take the third.
Yes. Yeah. Yes. Why don't you want to take the final?
I mean,
Because you have like a lot of other finals.
yeah, and you know, third exam is like, do we have a lecture after third exam?
Yes. Yeah, because whatever we don't cover, we'll go on the final. But it'll be very chill. It'll be very like, it's not gonna be anything like this. It's gonna be like fun stuff.
For
Like
fun.
interesting and fun.
Like relativity and quantum
Yes,
physics?
exactly, yeah.
For
Yeah,
fun.
yeah. It'll just be easy questions. It'll be
So it's not an option to take the third.
No, yeah, you have to take the final. You have to take the final, yeah. That's just the way it is.
Unfortunately,
Yeah.
and I won't go to the third exam.
Okay, that's fine. I'm glad you did that. I feel like a lot of people aren't, that's why we thinned out. You know?
Probably
They
just-
did well in the first two, like, you know, they did that part.
So the third one is just like drop.
Yeah, exactly. If the zero, I'll put a zero in and it just gets off. Yeah.
I appreciate it. Thank you.
You're welcome.
I just wanted to get clarification on the right-hand rule with the V, B, and
Yes.
F. Okay, so your thumb is V.
Yes.
So wherever V points, your thumb points in that direction. And then B would either be defined as out or in.
Yeah, well, I mean, your pointer will just point wherever B is.
Okay, yeah, wherever V is, and
Yeah.
then
Sometimes
for,
B is not in or out. It's just,
Okay.
I guess just the way the examples have been, B is
Yeah.
in or out, but it could also be up or down.
just wherever
Or
it points.
anywhere,
So
yeah.
your thumb goes wherever V is, index finger goes wherever B is.
Yes.
And then you turn inwards to find force?
Well, no, you don't need to turn. Once you've aligned these two,
Yeah.
then your middle finger will be in the force direction.
Okay, but you, like, initially, before you set it up, you point them like this, yeah?
Yes, yeah, you keep them like this, so imagine, imagine this is X, Y, Z.
Yeah, okay. That makes sense.
Yep.
All right,
Okay?
thank you.
You're welcome.
I have a question.
Yeah.
Since there is, I don't know if this would work.
Uh-huh.
Since there is magnetism like on the Earth.